So we have several different types of common reactions, and I've tried to categorize these in a way that kind of makes sense to you all. The first being a combustion reaction, which you've already done. So since we've already done that, I won't go through that very much, but just remember, whenever you have a hydrocarbon connecting with O2, you produce CO2, water, and energy, and that's actually the opposite of photosynthesis. Next, we have what's known as an addition or elimination reaction. It kind of follows with what the term says. Addition reactions add something to a compound. The easiest version of this is to consider a C-C double bond. There's different types of reactants that we can have here, but as an example, one more commonly used is one that's called a hydrogenation of alkenes, or a hydrogenation reaction. What this does is it adds H2 in the presence of a catalyst like platinum, palladium, nickel, and you put hydrogens right there where that C-C double bond is. Now, one thing to kind of note here, you've probably never seen H2 and PT like this over and above and below the arrow. When it comes to organic chemistry, we don't write everything out like you do for inorganic chemistry. We may not have a plus whatever it may be on the left-hand side. It may just be that we're saying you are telling people this is the reactant and it's under these conditions that you're reacting it. So we're not worried so much about exactly how much of everything you have. We're worried that a transformation takes place, and that's what you're massively looking at. What transformation takes place with the organic compound? So you may see things written to the left-hand side. You may see things written above or below that arrow. And another thing that you can commonly see is that sometimes we have H plus for an acid. Sometimes we have H3O plus for an acid. And sometimes we just identify an acid like HCl or H2SO4. All of these things mean the same thing, and that is, hey, an acid happens. Or you add an acid. It doesn't even necessarily tell you how much. That's something to keep in mind with these types of things. So an elimination reaction, back to our reactions, is actually the opposite of the addition reaction. So you could have something like a dehydrogenation of an alkane, where this hydrogen that's right, or the H over top of both of those carbons, is released from the carbon-carbon double bond that's right there, and that's what you produce, is you produce some H2. Now, that takes a catalyst to happen. In other words, it takes something that you're adding to the reactant to make that transformation happen, because that does not just happen willy-nilly, okay? So as a subcategory of addition and elimination reactions, I've identified several condensation and hydrolysis reactions. There's special things we have to pay attention to here. Now, when you're asked to identify the type of reaction something is, it can be both an addition or an elimination reaction, as well as a condensation and hydrolysis. And addition goes with hydrolysis, and elimination goes with condensation, just to confuse you. You know, that's the reason why. So let's go ahead and look at this. A hydration of alkenes basically means exactly what it sounds like. You are going to add water to a CC double bond. So you do that by separating it into an OH and an H, but that's where the water comes from. We've got H and OH added together, and that's where H2O comes from. Now, this is a nice symmetrical molecule. The reality is most things don't come like that. So there's something special that we have to apply, and that's called Markovnikov's rule. And the easiest way for me to see this is that when you're considering the H and the OH, and it has different places to go, the OH goes to the most substituted carbon. That's the carbon that has the most stuff it's attached to that's not hydrogen. So see how we've got a CC double bond right here? The carbon to the right has 2 bonds to other carbons. The one to the left only has, that other carbon that's attached to. So when given the option H2O, the OH is going to go to the carbon that's already attached to 2 other things. In a line bond representation, this H2O, all you see that goes to that double bond is the OH. That doesn't mean the hydrogen isn't there. We just don't represent it in this format. Another thing to note here, all of these reactions are using heat and H2O. My apologies, I did not write in heat here, but that is definitely there. Okay. Another way to represent heat is by drawing a triangle, as you see right there. Okay. So now let's talk about dehydration of alcohols. So you got to have an alcohol here in order to do a dehydration, because you're literally removing water, and the OH from the alcohol is combining with the hydrogen from a carbon next door. It must be a carbon that you can actually remove the hydrogen from. Okay. This is done with just an acid being there. So again, that could be H3O plus, it could be H2SO4. There's many ways to represent that. And what ends up happening is that this OH and the H end up making your H2O, and the CC double bond is there. So see how we go back and forth with these double bonds. Kind of cool. Now, the same way we had to consider Markovnikov's rule, when we do a dehydration of alcohols, we have to consider something called Zaitsev's rule. And what this is that when you're forming an alkene, the most substituted alkene will be the majority product. In other words, you remove the hydrogen from the neighboring carbon with the fewest number of hydrogens. Let's talk about that. This carbon right here has the OH attached. He can take that OH, can either remove this hydrogen or it can remove this hydrogen. Given those 2 options, the hydrogen that's removed is from the carbon that's the most substituted. So that's another way to look at it. So you end up with this CC double bond in the middle of the chain, because that's a more stable product, rather than removing the hydrogen from out here. Okay, so not this guy. You don't end up with that guy. Okay. So I look at this as you have to take the one from where there's the most like gang of friends. So we take this OH, it's gonna combine with the hydrogen right here, and that's why your double bond goes down towards that, where that substituent is, instead of away from it. Okay, now chances are you all need to go back and review those 2 categories. I fully anticipate that you're like pausing or going back right now to go back and review that. Try those examples again, okay? You should. I'm going to keep going forward, and I hope that we're sort of starting this again at this point. So esterification is kind of its own version of a dehydration. It's still going to be like an elimination reaction. And here, what we have is we have the OH from a carboxylic acid that combines with the H from an alcohol in order to make water. And as a result, we get this CO bond right there, and it's in the middle of a chain. Now, acid hydrolysis, which would still be like addition, or you can consider that even a hydration reaction, we basically use the same thing along with water. in order to separate an ester. Now, what the beauty of this is that means that we could both make esters and remove esters or tear them apart. And pretty much you're using the same thing. Where the difference is how much water you have. And we can talk about that a little bit more in class because I realize that these are hard to see right now. So let's go for that. Okay. The next major category is that of oxidation and reduction reactions. These aren't so bad. Basically, an oxidation reaction adds more bonds between carbon and oxygen, at least in organic, that's the way to look at it. And a reduction reaction removes bonds between carbon and oxygen. But there's certain ways that we can have those bonds be present. So if we start by looking at a primary alcohol, what that means is like the carbon that's attached to this OH is only attached to one other carbon. So it's on the end, okay? And we just represent this by, hey, we're going to go through oxidation. You don't need to worry about any more than that right now. The first step in adding bonds to that CO bond would be to have a double bond right there. And if we keep undergoing oxidation, in other words, it keeps going, the reaction continues to go, then what we end up with is a carboxylic acid, because you can't have a CO triple bond, at least not as far as what you all know. If instead you're having a secondary alcohol, in other words, this carbon right here is attached to the middle of a chain, then we add a C-double-O bond right here. We add a bond between another C and oxygen. But at this point, the carbon that's involved right there cannot undergo any more reactions. He's got 4 bonds. He's done. So you can't actually add more bonds than what carbon can take. And this is what happens with a tertiary alcohol too. This carbon right here, if you undergo oxidation, there's no reaction that can take place because it can't bond more than 4 times. So when you run out of bonds that carbon can have, you're done. That's it. Stop. Okay? This also is similar to what happens if you start with a ketone or an aldehyde. If you start with an aldehyde or a ketone. If you start with an aldehyde, oxidation can occur because there's another bond that's left there. And yes, there's always bonds that are left there. There's CH bonds. You can remove a CH bond in order to replace it with oxygens. You just can't do that for a CC bond. But when it comes to a ketone, you can't do that because that carbon's already bonded 4 times. We can also oxidize what's known as a thiol, so SH groups. And we do that by making disulfide bonds. Yeah, I know he's weird, he's different. So that can happen. Now, reduction is the opposite. So if we're reducing something like a carboxylic acid undergoes reduction to make an aldehyde, which can undergo reduction to make an alcohol. If you have a C-double-O bond and that undergoes reduction, either of the aldehyde or ketone, you end up making an alcohol. The difference is a primary alcohol versus a secondary alcohol. And just like we have with disulfides, if we undergo reduction there, you end up with a thiol. So there's this other category called hemiacetyls and acetols. We're going to talk about that later. That's a little bit more. Okay. Finally, we have what's known as acid-base reactions. Now, for the purposes of what you all need to know at this point, we're going to talk about that being the exchange of H plus or OH minus. That's a very general categorization, but we're going to go with that, okay? Please mark your unpaired electrons here. It's going to help you. And as we sort of talked about already, nitrogen has 2 lone pairs of electrons here. It can take on this H plus. Now, sometimes that's represented this way, just warn you. And that ends up giving you a positive charge right here on nitrogen. Or if you have something that's got a negative charge, like a carboxylate, this negative charge can combine with an H plus, and that'll give you or a carboxylic acid there. The opposite can hold true as well. If you have a carboxylic acid, like we talked about before, and you add a base to it, then that removes this hydrogen right here, because that's what makes water. Or if on the other hand, you have this guy right here, this OH or base will combine with a hydrogen. It could be either hydrogen, it doesn't matter. And that will give you water. Okay. Acid-base reactions, I think you all have seen a little bit more of. So these might be a little bit easier, but you have to follow your charges here. So make sure that you're keeping up with that. Thank you very much. I hope this helps. You will need to watch this more than once in order to get these. That's normal. Try going back and, writing down what reaction you have and seeing if you can find the product. Okay. Thank you very much.